All right. Thank you, everyone, for being here. There we go. So the name of my talk is Exploring the Role of Active Black Holes in Galaxy Evolution. So when I first learned that I was going to give a talk here, I got concerned and I thought, how could I make people care about black holes? You know, they're really just boring objects, aren't they? But lucky for me, in the news last week, there was a very big announcement that was all over the news and all over social media. And that is the first ever image of a black hole observed by humans was released. Yeah, it definitely deserves a round of applause. Now, I'm sorry to say, I'm only going to be talking about how black holes affect the galaxies that they live in. I'm only going to say a few words about this image. However, this is really exciting because what we see in the image actually lines up with a lot about what we understand about black hole physics. Now, astronomers have been simulating black holes for a little over a decade now, but have never really had an image or an observation to compare these simulations to. So for the very first time, astronomers can compare their simulations of black holes to images of an actual black hole, and this is completely going to revolutionize what we understand and know about black hole physics. So this black hole is, I don't know how much you guys know about this black hole, but it is located at the center of the galaxy M87, which is a galaxy located about 55 million light years from Earth. And it is part of a system known as an active galactic nucleus, or an AGN. An AGN is a compact region inside the center of a galaxy where matter such as gas, dust, stars is actively accreting onto the black hole. But it doesn't just fall into the black hole, it really swirls around into the black hole, and this black hole has such strong gravitational potential that it shreds up the matter that's falling on it, and so this matter reaches very high luminosities, very high temperatures, and so it's very bright. This is an image. I don't know if you guys have seen this image, but this image has also been making the rounds lately. And this is a picture of the AGN inside M87. This is an X-ray image. And so as you can see, it looks quite chaotic, very bright. And this is a zoomed in picture of that same AGN. And it looks, it's very bright. You can see that there's a little jet emanating from the center of the black hole right here. The black hole would be located right here, and here's the jet. And this jet is something that's typical in a lot of these AGN systems, and I'll say a few more words about that. So our understanding of AGN is that there's three basic components that build these things. First, you have an accretion disk. This accretion disk is a disk full of matter, gas, stars that are falling into the black hole. Now, this accretion disk is dominated by very powerful physics, so it actually is very bright, radiates at UV to optical frequencies, and you can see these objects from very far away. So in a lot of cases, the light from these accretion disks can actually outshine the galaxy light, so they're very powerful. Next, you have what is known as the relativistic jet. So this jet, it's extremely powerful. It can extend up to several million light years away from the black hole. So you can only imagine how powerful these jets must be in order to actually extend that far from the black hole. These are most commonly seen at radio frequencies, but they can be observed, of course, at X-ray frequencies, optical, and so on. Lastly, you have the innermost stable circular orbit. This is the inner edge of the accretion disk. Any matter that goes beyond the innermost stable circular orbit is immediately devoured by the black hole and is lost from the universe forever. So again, this just marks the inner edge of this accretion disk. So next, I just want to show a simulation of the Milky Way black hole. Now, the Milky Way black hole, Sagittarius A, is not actively accreting matter at this moment, but it was believed to have done so about 10,000 years ago. And so I just wanted to show this video because A, it's a cool video, and B, because when you see the accretion falling onto the, when you see the accretion falling onto the black hole right here, you can see that there's winds and powerful jets stemming from the center of the black hole. And so as an astronomer, I'm interested to know are these winds and jets capable of affecting galaxy evolution? Are they capable of shaping the galaxies that we see today? So when we look at galaxies, in the sky, galaxies come in all shapes and forms. We have young starburst galaxies, which are these young blue. These are these blue dusty galaxies you see up here. You can see that they look really real disk-like. And this one itself has an AGN jet, that you can see right here. It's very cool. And so you also see old elliptical galaxies. It's these spherical galaxies that you see at the bottom. They're very red. They have old stars. They have little to no episodes of star formation going on. So I want to know, is it possible for AGN to perhaps convert some of these starbursty stars into old elliptical galaxies through some AGN phase? Now, there is motivation for this question. We're not just asking, oh, can AGN possibly do this, shape galaxies this way? The motivation comes in the form of something astronomers call the stellar mass function, which is shown right here. Now, I know there's a lot going on right here, so bear with me. This y-axis here shows number density of objects. This x-axis right here shows galaxy stellar mass, which is the mass of galaxies entirely made up of stars. So for reference, the Milky Way has a mass of about 100 billion solar masses. So that would place it like right around here on this plot. So this is showing us the number density of galaxies in the universe as a function of stellar mass. These solid lines are data from simulations. The squares, circles, and triangles are data from observations. So, so what we're seeing here is that the number density of galaxies increases towards lower stellar masses. So the frequency which we observe them increases towards lower stellar mass. And as you move to higher and higher stellar masses, these galaxies actually become less frequent. Now, the real mystery is, why is there such a steep decline here past 10 to the 12 solar masses? There's no reason, really, why galaxies shouldn't stop growing beyond this mass. Like, why aren't we seeing galaxies, with masses higher than this? And so we believe there's a mechanism that is affecting the growth of these galaxies. And what we believe this mechanism could very well be AGN. AGN have enough energy output. They're powerful enough in order to be able to affect the growth of galaxies. So AGN can halt, suppress, prevent galaxy growth through jets, winds, radiation. The collective term for all of these is simply known as feedback, or AGN feedback. This AGN feedback can heat the gas or destroy the gas that provides the fuel for future star formation in galaxies. So it's very powerful. However, the problem is the exact physics of how this occurs remains unclear. Now, the reason being is because a lot of these jets, or these radiation, these winds, sort of stem from the accretion disk of the black hole. But this accretion disk is about a millionth the size of the total galaxy. So it's a real mystery to us just how an AGN can produce winds that are powerful enough to really prevent the growth of an entire galaxy. So my research focuses very much on trying to answer this question. I want to know just how AGN can really affect the growth of a galaxy. Now, unfortunately, we don't have a clear-cut answer right now. We are working on it. But I do this by looking at something known as the connection between AGN and star formation across time. So this is a plot from my own research. Here on the y-axis, I'm showing star formation rates. So star formation rate is, of course, a measure of the rate at which a galaxy is growing. On the x-axis, I have stellar mass. These colored points are galaxies without AGN, so it's a representative sample, if you will. And the black stars that you see right here are AGN galaxies. These dashed lines form what astronomers call the main sequence. So most of the galaxies that you see actually have star formation rates that fall on the main sequence. And we would say that galaxies with star formation rates above this main sequence have enhanced star formation. Galaxies below the main sequence have, suppressed star formation. Oh, and something I didn't mention was that each of these panels represents a different epoch in the universe's age. So in the lower right-hand panel, this shows galaxies from when the age of the universe was about 3 billion years old, 4 billion years old, 5 billion, 7 billion. You get the idea. So one thing that we can see from this plot is that when the universe was about 3 billion years old, most AGN have star formation rates that lie above the main sequence. That is, they have enhanced star formation. But as you move forward in time, these galaxies start to have, these AGN galaxies start to have star formation rates that populate the main sequence. And even as you move to the age when the universe was 7 billion years old, that is roughly half the age of the universe today, you can see that they really have many more galaxies with these suppressed star formation rates. So looking at these results, it's really difficult to say, oh, there is this certain process in which AGN are affecting the star formation rates of their galaxies. But we can use these results to compare to theory and use that to constrain the physics of AGN and galaxy formation. So we can use these results to constrain, as I said, models of galaxy formation in AGN. For instance, these results can tell us the level of AGN activity expected in starburst and star-forming galaxies. AGN activity is something that can be measured through X-ray emission, and we have X-ray data for our AGN galaxies, so this is something we can already start to do. These results can also tell us about characteristics of AGN in star-forming versus quenched galaxies. Quenched is just astronomer jargon for galaxies that are no longer forming stars. They used up all their gas, they can no longer form stars, and so we call them quenched. Lastly, these results can also tell us how levels of star formation and AGN activity evolve over time. So the next steps, with these results would be to hand them off to some theorists, and then to have these theorists tweak forms of AGN feedback in their models such that their simulations obtain results that match our observed results. So in other words, these theorists are going to constrain the AGN feedback. We're going to learn about the AGN feedback through this way, and they want to reproduce a distribution of galaxies that look very much like the galaxies that we see today. Okay, so I just want to leave you guys with a short summary about what I talked about. Winds, jets, and radiation, known as feedback, that are released from an AGN can affect galaxy growth, but the exact physics of these processes remain unclear, and we can constrain our understanding of AGN in the following ways. We can study nearby systems with AGN, like M87. Of course, M87 is actually not that nearby. It's about 55 million light years away, but it is much, much closer than any of the objects that I'm interested in. You can study the relation between AGN and star formation across time, much like I do, and we can use this then to tweak black hole and AGN physics and models to achieve a simulation that resembles something like the observable universe. Okay, that is it.
Thank you, Jonathan. All right, the way this is going to work, if you have a question, raise your hand. We'll call on you. You can ask your question. Hopefully one of us will remember to repeat the question, yes, and then Jonathan will give an answer. But before we start, we are going to start with a Twitter question from Ilava Sam. He asks, in the simulation that you showed of the accreting black hole, the animation showed the stuff falling into the black hole anti-clockwise or counterclockwise perhaps when falling into the black hole. Is that always the case, or is there what determines how it falls into a black hole?
So unfortunately, I cannot say whether there is one way in which all black holes or the accretion disk around all black holes are spinning. That is a question, of course, left up to the theorist. My current understanding is that no, there is no reason why it's rotating clockwise or counterclockwise.
All right. Yeah, it probably just depends on the angular momentum or something of how stuff is infalling.
Of course, the angular momentum of the gas that's falling in, that's the rotation it's going to adopt.
All right. How about some questions from the audience? We'll start with you, sir.
Okay, he asks, what is it that causes the AGN to be more or less intense? And this is simply the amount of matter that's falling into the AGN. As the amount of matter that falls into the AGN increases, you're going to have a higher number density surrounding that black hole, so more matter is going to get shredded. It's going to become more luminous, more powerful.
All right. How about you? And then we'll go to the back.
Yes.
So did we just miss our galaxy being an active black hole?
Basically, so there is a lot of, oh, sorry, I should repeat the question. So he asked that when I showed that simulation of the black hole, I said that there was matter falling into that black hole about 10,000 years ago. So did we essentially just miss, having been able to observe the matter falling into this black hole? And the answer is the black hole of the Milky Way actually shows a lot of variability, unlike other types of AGN that we know of. And so it actually varies on very short timescales. And astronomers are right now on the lookout for a gas cloud that's actually close to the center of the black hole. And it's very possible that we'll be able to observe it in our lifetime. It might not be as exciting or as energetic, as maybe the event that happened 10,000 years ago, but it is something that astronomers are hoping to observe in the next couple of years.
All right. You in the back sitting down?
Yes. You spoke to the edge of the accretion disk near the black hole.
Yes.
Could you speak to the difference between the event horizon and the photon sphere? And in addition, if I wanted to learn about that geometry, space-time geometry, do I need to know all of Einstein's field theory?
Okay, sorry, that's, how can I repeat that one? Because that was a long-winded question. He asked if I can talk about the photon sphere, the event horizon, the accretion disk, and sorry, what was that the last part of that question?
If I wanted to learn, I'm kind of a citizen scientist, but I want to learn more.
Okay.
Especially about the space-time around black holes. How much of general relativity do I need to know?
You need to learn everything about general relativity. I don't even understand, really the math that goes into computing that. But you asked about the photon sphere. That is the innermost edge of the accretion disk. This is where matter is at its most powerful, because the gravitational potential there is so high that matter is just reaching really high temperatures. And so it is emitting very energetic light from that photon sphere. And as for the event horizon falls just a little bit further in of the photon sphere. Don't really know what else to say about that, but one interesting tidbit of information that I recently learned was that image of the M87 black hole that we just saw. What we're actually picturing there is the event horizon, not the actual black hole, because the black hole is a singularity. It's a single point inside that, that bubble that you see. And that event horizon is about the size of the solar system. So I thought that was very interesting. Yeah. Okay.
Yeah, if you want to simplify your life, I do know that if you just only think about non-rotating black holes, then I think the photon sphere and the event horizon are the same thing, right?
They pretty much are, because if it falls beyond that, then it's pretty much sucked up by the black hole.
Right, but if it's spinning, then it gets hella complicated. All right, let's see. Anything in the balcony? Else we'll try at least one more in the back, towards my left to the right. Yes.
So you kind of talked about stars and other systems falling into M87.
Yes.
How about the two black holes in Andromeda? They're locked down to each other.
I'm sorry, could you repeat that? How are the what?
The two black holes in Andromeda.
Oh, I have to apologize, but I do not know much about the two black holes in Andromeda. Was there a certain question you had about them?
Like they are falling onto each other, is what I understand.
They will eventually merge and collide and form, an even bigger black hole, if that answers your question.
Yeah. But
Yeah. No, sorry. So one thing I didn't mention, my research has very little to do with the black holes that we see in nearby galaxies. I'm actually interested in AGN that are millions and millions of light years away. They're extremely far away. And so unfortunately for me, I don't get to take close-up action shots of these merging black holes. So unfortunately, I can't say too much more about those. Yeah.
Maybe we have time for, excuse me, one more question. Up in the balcony.
So he's asking if there's a low pressure area around the jet of the AGN that is causing it to extend so far out. Is that correct? Yeah. So yeah. So those jets are actually relativistic. It's not necessarily a low pressure area above the black hole. Those jets are just so incredibly powerful that they will extend very far beyond, the distance, like the size of the galaxy. So as I said, they can extend up to several millions of light years from the galaxy. In a galaxy, they're just not that big. So it's more that they're very powerful. There isn't necessarily a low pressure region above the black hole that's causing this.
All right, Jonathan, I think we'll be around during intermission if you have any more questions. So let's give him another round of applause.